Hi, this is the video for section 3.4 of A Student's Guide to the Schrödinger Equation. In this final section of chapter 3, we're going to talk about the three-dimensional Schrödinger equation. In order to extend the Schrödinger equation from the one-dimensional version in which we had a wave function psi of x and t, we're now going to write psi of r and t, where r is the position vector defined by x steps in the I hat direction, y steps in the j hat direction, and z steps in the k hat direction. In addition to using the vector r instead of the scalar x, we've also got to use a vector version of the wave number k. That's defined by this relation, in which you can see that now the wave number, instead of simply being 2 pi over lambda and the direction assumed to be along a single axis, now the k vector can point in any direction depending on the components, k sub x, k sub y, and k sub z. You can see what that looks like in this figure, in which this is a plane wave propagating along the y-axis, but this is a plane wave propagating in a general direction. The magnitude of that wave number is just given by the square root of the squares of the components, and that still equals 2 pi over lambda, exactly as we said in the one-dimensional case. So if we're going to put that vector k in and the vector r instead of x, our wave function psi looks like this. It's now a function of r and t, and notice that in the exponent, where we used to have kx, we now have k the vector dot r the vector, the scalar product between those two vectors. If you're wondering why we have a dot product there, I think that's best explained if you imagine these planes of constant phase. This one happens to be a plane wave propagating along the y-axis, but applies equally well in any direction. And what you see here is that the position vector r, I've shown 3 of them here. If I take a plane that is essentially the xz plane here passing through the origin, notice that all those position vectors must be perpendicular to the wave vector k, which, as I said, in this case is propagating along the y-axis. So in that case, the vector k dotted into the vector r is going to give 0 because they're perpendicular. Cosine of 90 degrees is 0. So k dot r equals 0 defines this plane. And now look at the next plane. You can see that here. That second plane, what does k dot r mean there? Well, remember, with k dot r, we're projecting one vector onto the other and multiplying by the magnitude of that second vector. So in this case, if I project r down onto the direction of k, notice all of those projections have the same magnitude. So therefore, k dot r will not be 0, but it will be constant. That is, it will have the same value for every point on this plane, just as it had the same value of 0 for every point on this plane. And if we had done a third plane, all of the points on this plane have a different but constant value of k dot r. There's an explanation here of exactly what that mathematics looks like. Here's k dot r written as magnitude k, magnitude r cosine theta. And since the magnitude of k is 2 pi over lambda, when you multiply the distance r cosine theta, that is the projection of the position vector onto the direction of k, by k, you are essentially dividing by lambda, so that turns that distance into a number of wavelengths, and multiplying by 2 pi, and that converts it to radians. So it's summarized here. It says k dot r gives the distance from the origin to the plane in units of radians. In other words, it gives you the phase variation that that wave will experience in propagating from the origin to that plane. If you want to write out what k dot r is, you can put in the components of k and the components of r, do that dot product, and there's the result. Plugging that in gives this expression for psi of r and t, and that's what our three-dimensional wave equation is going to involve. But we've also got to think about that second derivative with respect to space term. In the one-dimensional case, it was just the second partial with respect to x. But now we've got to consider y and z. So here we take the first partial with respect to x. We notice it brings out an ikx. Taking that second partial, just as it did before, it brings out a minus k sub x squared. But what if we do the same for y and z? Here's the second partial with respect to y. Here's with respect to z. Now add those together. Here's the x part, there's the y part, there's the z part. Here are the three results of those derivatives, and look at what we get here. This is just minus the magnitude of k squared. So we can write the sum of those partial derivatives as equaling minus k squared times psi of r and t. And that can be written as an operator. Notice we've gathered up these partial derivatives here, and we're going to let them operate on psi. There's a name for that operator. It's called the Laplacian operator, and the rest of this section's going to have a lot of discussion of how the Laplacian works. The notation you usually see is as the del squared operator, second partial with respect to x, y, and z. That's the Cartesian version. As it says in a footnote down here, sometimes you'll see it written as a triangle instead of del squared, but I think this is by far the more common version. Okay, we can plug that into the Schrödinger equation, where we formerly had the second partial with respect to x only. When we do that, here's our three-dimensional version of the Schrödinger equation. Notice the differences. Psi of x and t is now psi of r and t, and this Laplacian operator has replaced the second partial with respect to x. Clean this up a little bit. So this is a version of the Schrödinger equation that you're very likely to run into in other quantum books. And how do we interpret that three-dimensional version? Just as we did in the one-dimensional case, I think it really helps to look at the three-dimensional version of the diffusion equation. But now we have, instead of f of x and t, we have f of r and t, and there's our Laplacian, where we formerly had the partial with respect to x. We still have the diffusion coefficient, and comparing these two equations, we see how similar they are. But of course, we do have the I factor, and just as in the 1D case, that's going to have important implications. But first, I think it's helpful to look at that curvature in the three-dimensional case. And I do that in the rest of this section in two different ways. One is by looking at it as an operator that compares the value of a function at a point to the value at the surrounding points. But also, we're going to look at it as the divergence of the gradient. So we'll get into that in a minute. But first, comparing it to the average. How do we do that? Well, even though this is the three-dimensional discussion, we're going to go back to the one-dimensional case very briefly, and I want you to consider psi of x over some range of x, and we're going to look at the value at what I call x0. There's the value at that point. And imagine that this function has no curvature. That is, the change in the slope is 0. If that's true, then if I go a little distance delta x to the right and a little delta x to the left, look at what I get. I get the value of the function that's here and the value of the function that's here. And the value in the middle, that is at x0, is exactly equal to the average value between the points here and here. But what if the function has, in this case, positive curvature? Here's that function. Notice the slope is increasing. It's positive curvature. Slope is positive and increasing. Now what if I take the value at x0, then I go delta x to the right and delta x to the left. Now look at what happens. The average of the value at those 2 points is somewhere up here. But at x0, the value is less than the average value at the surrounding points. Notice we've gone an equal distance left and right, but the function has changed more in going to the right when we have positive curvature. So in this case, the value of psi at x0 is less than the average at the surrounding points. Now take the opposite case. Here's negative curvature. Slope is positive, but it's getting less positive. So that's negative curvature. Now when we look at the value of the function at x0, we get a value. If we go a little bit one direction, we get a bigger, but not much bigger value. If we go the same distance in the other direction, we get a value that's considerably smaller. So now the value of psi at x0 is bigger than the average of the surrounding points. So that's another way of interpreting what positive and negative curvature are telling you about the value of the function. It's summarized in this little paragraph, which says, the curvature of a function at any location is a measure of the amount by which the value of the function equals, exceeds, or falls short of the average value of the surrounding points. Okay, that's fine for one dimension, but what about a two-dimensional function? Well, let's look at this case. Here we see a peak, and here we see a valley. Consider the value of the functions psi of x and y right at the peak. Clearly, at this peak, that value exceeds the value at surrounding points. In this case, those surrounding points make a circle around this cone, and clearly the value at the peak exceeds the value of the surrounding points. But in this region, this has negative curvature. So the Laplacian is negative at this point, and the value exceeds the value of the surrounding points. In this case, we're at the bottom of a valley, and the value of the function at that point is clearly less than the value of the surrounding points. And this one has positive curvature in that region. So once again, as it explains here, the curvature tells you whether the value at a point equals, exceeds, or falls short of the value at surrounding points. But as I mentioned, there's another way to look at this. And to do that, we need to talk about these differential operators, gradient and divergence. Probably ran into these in an E&M class if you ever took one of those. And of course, in colloquial speech, gradient just means some kind of change, usually over space, such as the change of height on a road that has a slope, or the intensity of the color in a photograph, temperature in a room. Gradient generally means change over distance. And if you write out an operator for the gradient, it's this del operator. There's a little arrow hat on top because what it's going to do is produce a vector. Here it is in 3D Cartesian coordinates. There's an I hat, j hat, and k hat component, and each one has a relevant partial derivative. So if I feed this a three-dimensional function of x, y, and z, it looks like this. Notice we're taking a scalar function, psi, and we're turning it into a vector by applying the gradient operator. So what is it the gradient tells you? The direction and the magnitude are both important. The direction tells you the direction of steepest increase in the function. If you think of these heights of the ground, it tells you which way is the steepest uphill direction. And the magnitude of the gradient tells you how steep it is. That is, the rate of the change of the function in that direction of steepest increase. So if we apply it to our psi of xy function here, these arrows are the gradient arrows. Notice they're all pointing uphill in the direction of steepest increase. But what if we have a valley function? Again, they're pointing uphill. They're pointing the way out of the valley. I think it's helpful to see these from a top view. So now we're looking down on our positive peak and down on our valley. And notice the gradient vectors are pointing in toward the positive peak and away from the negative peak. I've also put in some lines of constant value. You can see that the gradient is perpendicular to those. And here it talks about why that's useful because of the next operator we want to talk about, which is the divergence operator. Here's the definition of divergence. Notice now we're taking the dot product of this del operator, which is a vector, with A, which is a vector. And when you make that dot product, multiply the x components, the y components, the z components, look at what you get. A scalar result that includes the change of the function with each of the three directional variables. So, what does that tell you about the function? It tells you whether the function is diverging or converging at that point. Diverging and converging, a lot of people use them as spreading out or coming together. It is slightly more subtle than that, but the way to understand it, I think, is to think of this as velocity vectors in a fluid that's flowing. If the divergence is positive, more fluid flows away from that location than toward it. So you would think of a source of fluid as existing at that point. If the divergence is zero, then the fluid away from that location is exactly the same as the fluid flow toward that location. And if you have negative divergence, then there's more fluid flowing toward that point than away. You would say that's a sink of the fluid. Of course, in quantum mechanics, we're not going to be dealing with actual fluid flows, but this idea of understanding the divergence, that is, if you imagine at the point of interest some tiny sphere and imagine whether the outward flux of the vector field is greater than, equal to, or less than the inward flux, that's helpful for the divergence. The thought experiment usually used for this is to imagine sprinkling some sawdust or powder on the fluid, and if that sprinkled material disperses, that is, if its density decreases, you're at a location of positive divergence. If the material compresses, the density increases, you're at a position of negative divergence. So what does this have to do with the Laplacian? Well, look back at our gradient vectors. Clearly, they're converging on this point, which has a value exceeding the values of its neighbors. And they're diverging away from a point at which the value is less than the values of the neighbors. So the divergence of the gradient is positive here and negative here. And that's exactly what the Laplacian tells you. So here it is, written as the divergence of the gradient. When you apply those derivatives, you get our Laplacian back. So what does that have to do with diffusion? Well, remember, we said the time rate of change is proportional to the Laplacian. That means if you've got, for example, temperature in some 3D region, and that temperature exceeds the average temperature at surrounding points, the change in that function is going to be negative, and therefore it's going to cool off. Whereas if the average of the temperature is lower than the average of surrounding points, the Laplacian is positive, that's going to heat up. Okay, can we just blindly apply that to the Schrödinger equation? Well, once again, that I turns out to mean the solutions are going to be more complex than simply diffusing. We're also going to allow solutions that oscillate, and you'll see plenty about that in the next 2 chapters. But before we get there, let's take a look at the time-independent version in which we separate out a function only of position, in this case, position vector r, and time t. We can do the same analysis we did previously, plug that in to the Schrödinger equation, solve for the time function, and we get this time-independent Schrödinger equation. But you can recognize the 3D version because it's got the Laplacian instead of the second partial with respect to x only. If you want to use the Hamiltonian operator, you can write h hat like this, involving the Laplacian. And just for completeness, since we've looked only at the Cartesian version here, I also provide the spherical coordinate version of the Laplacian, which looks like this. All right, as always, the last section in this chapter is a set of problems. Full solutions available on the app and on the book's website. And I strongly recommend that you work through these before you proceed on to the next chapter. Once you do that, you should be ready to go with the solutions to the Schrödinger equation. Good luck.